So every time I'm uploading a updated version of the notes on the Dropbox folder. There's tiny changes, but if you want the last version, it's usually 10 minutes before the class. No major changes, just one extra figure, or I correct a typo or things like that. Anyway, so what we did the last time was to look at the topographic effects on the western boundary currents. So in the Stommel and Moog problem, we were considering linear bottom drag or horizontal biharmonic friction to explain the balancing vorticity. And we always took the ocean to be a flat bottom. But obviously that's not the case. Sidewalls, they have a slope. And so we looked at the effect of that slope on the depth integrated ocean. And so we derive what is called the bottom pressure stress. Okay, so now we define a topography H, which is a function of space, x and y, and consider a stratified ocean. So there were both the effect of topography and the fact that the ocean is stratified, is not homogeneous anymore. So we took the planetary geostrophic approximations and equations, which is those momentum equations there. We integrated over the vertical, and we got this expression. Okay. We used the Leibniz rule to look at the vertical integral of the pressure gradient, of the pressure term. Which looks like that, and after you put the expression of the vertical integral of the pressure term into the vertical integrated momentum equation, then it looks like that equation over there. You can rewrite the vertical integral of the pressure this way, and then there's an extra term here, which is potential energy term, due to the fact that the ocean is stratified. Right? And then vertically integrated momentum equation then become blah blah blah. You substitute with these two terms, and finally you have these terms over here. Okay. And so this extra term arises because of the fact that the ocean is stratified, and then this extra term arises because there is the ocean is not flat. So the pressure gradient doesn't go to zero after vertical integration. So you can take you can obtain a vorticity balance of this after you take the curl and you introduce the stream function definition, and you have this nice equation with it, okay? Where you have the potential energy term, the topographic term. If you make the ocean homogeneous, so not stratified, E goes to zero. Or if the bottom is flat, H is a constant, and so you recover the Stommel problem. And so this term, the extra term, due to the fact that you have stratified ocean and topography, is what is called the Gerber term. Okay? So joint effect of paraclinicity and relief. And because of that term, you have an extra term in the vorticity balance. If that term vanishes, then you recover the Stommel problem, which is simply this, okay, a balance between the wind stress curl at the surface, some diffusivity term, which could be bottom drag or horizontal friction, and the advection of planetary vorticity beta. Okay. An alternative derivation, including the effect of topography, is getting rid of the potential energy term. So after you take the curl, you get rid of the energy term, and you end up with the vertical integral of the meridional velocity equal to the curl of the forcing and this term, which is called the bottom pressure stress curve. Okay, is the fact that you have a bottom pressure which is not vanishing because topography is not constant. So that term is the bottom pressure stress curl or foam drag curl or bottom pressure torque, okay, whatever you want to call it. for a homogeneous, frictionless and unforced gyre. So this goes to 0 because it's not forced and is frictionless and is homogeneous, so there's no stratification. Then the only terms that are left are the advection of planetary vorticity, beta v, and this term over here. Okay. So that means that even if the gyre is not forced and there is no friction, you can induce a meridional flow just because you have a pressure gradient, because after you vertically integrate, the pressure gradient doesn't go to 0 because you have a bottom relief. So that bottom relief maintains a pressure gradient, and if there is a pressure gradient, there can be a meridional flow. And so the meridional flow is driven by the curl of the foam drag, just as the meridional flow was driven by the curl of the wind stress of the surface. If you have a no constant topography, the curl of that foam drag term can drive a meridional flow. So obviously, if you return to the case of a flat bottom ocean, you can only have a meridional flow if the flow is forced at the surface or if there's friction. Otherwise, the vertical integrated velocity goes to 0. Okay, so if you look at that term, so you consider an ocean with both force and friction are absent, so unforced and frictionless, and assuming a homogeneous gyre, then the vorticity balance simplifies to that Jacobian. Okay. And so what that Jacobian means is that the stream function psi is a function of that term f over h. Okay. And so in the depth integrated scale, the stream function, all the streamlines will have to be parallel to f over h in order for that Jacobian to be 0. Okay. So if you have a meridional flow, the streamlines of that flow will have to be parallel to f over h contours. And so in an unforced gyres and frictionless, that is called a free mode, free in the sense that it's not forced by any forcing of the surface and is not forced by friction. The meridional flow exists simply because there is a relief at the bottom. So in that sense, it's called free. So that's a free mode. And so again, this is a statement about the balance between the vortex stretching, because if you imagine that column of water vertically integrated going down a slope, then the column of water is stretched or shrinked because of the change in topography, and that column of water will not change its relative vorticity because we're talking about large-scale circulations. And what we'll do in order to conserve potential vorticity is to change planetary vorticity. And so as it goes down a slope, it will try to conserve potential vorticity, and will do that by changing planetary vorticity. So it will induce a meridional flow. That's why topography can induce a meridional flow just by conserving planetary potential vorticity. Okay, so there's an example there. Blah, blah, blah. And so if you look at the f over h contours, they look like this in reality. Okay, so they are following latitude circles close to the equator. But if you go close to the western boundary currents, you see how they are close together and they're actually not parallel to latitude circles. And so in those regions, if the bottom pressure torque is dominating, then the flow will follow those f over h contours. Okay, so if you do a numerical experiment of this and you try to quantify the importance of each term, the wind stress curl at the surface, the friction at the bottom or at the side, whatever you want to do, and the J-bar term, so the bottom pressure stress curl, then you see that the bottom pressure stress curl, in a simple case where you have sloping boundaries on the west, which is like close to reality, then the only place where that term is important is close to the western boundary. Okay, those shaded regions. Those regions is where the bottom pressure stress curl is important and has to be taken into account. And that's the region where the f over h contours, they deviate from the latitude circles. And so if you have a flat bottom ocean on the left or a ocean with a sloping western boundary current, you see the difference in the in the solution for the wind-driven gyres. In one case, they are totally symmetric. You have a western boundary current, but it's totally meridional. Whereas in the second case, the western boundary current has a slope, and that slope is actually following the f over h contours, because in that region, that term is dominating. Okay. So since we're talking about vorticity conservation, you can look at the linear vorticity equation, which is this one. Okay. And if you vertical integrate this vertical velocity doesn't vanish because vertical velocity is not zero at the bottom anymore. You have a bottom topography. So now you have three terms. On the right hand side, you have the change in planetary vorticity, which is the response, and the meridional velocity induced by either the wind stress curl or the torque by the bottom friction or horizontal viscosity, and the stretching of the water column induced by the change in topography. Okay. So in one region, one term might be dominating and causing the advection of planetary vorticity. In a different region, another term might be dominating. So you have these four terms, and if you actually look at a numerical solution, then you see the case of a homogeneous topography on the left, and the case where you have a sloping western boundary on the right. Okay. The dotted lines are the f over h contours. And now you can see the balance between the terms in the vorticity balance. So in the interior, you have a balance between wind stress curl and the advection of planetary vorticity, which is the Sverdrup balance. Then here, close to the bottom left, is where you're trying to close the streamlines and start the return boundary current, returning all the Sverdrup flow to the north. And in this region is where you have to cross the f over h contours. Okay? So you cannot be, the bottom pressure stress curve cannot be dominating, because in that case you have to follow f over h contours. So the only way to cross f over h contours is if you have friction that allows you to cross those f over h contours, which is what you're doing in a case of flat bottom. Okay? In a case of a flat bottom, you're crossing f over h contours all of the time, because friction is providing you the balance in the western boundary current. Okay, that's the Stommel and the Moog problem. You have the Sverdrup interior, where friction is negligible, and you have a frictional boundary layer on the west. Okay, which allows you to cross the f over h contours, which in that case they're just f contours. Okay? If you have a sloping boundary, then the f over h contours, they look like this. So the only place where you need friction is here, when you're crossing the f over h contours. The bottom pressure stress curl is not dominating, you're not in this Sverdrup interior, so you need friction in order to be able to cross these f over h contours. Once you cross them, then you don't need friction anymore. The bottom pressure stress curl provides you the input of vorticity in order to change your planetary vorticity and return all the flow, in this case, to the north. And you're doing that by following f over h contours, which are not meridional anymore, but they bend in this case, just like in reality. And so now the wind-driven gyres, they look more like this. They're not symmetric, and that's because they follow f over h contours. So now the western boundary currents is not a frictional boundary layer anymore. You just need friction in a tiny place in order to cross the f over h contours. So the need for friction is not that justified anymore. Okay, so if you do a more realistic simulation, you have the one on the left, where you don't have bottom topography. You just have this Sverdrup solution, and you then add linear bottom drag. If you add topography, you get the solution on the right, which is much more close to reality. You have a Gulf Stream that is turning into the Atlantic Ocean, is detaching from the coast, and is actually following F over H contours. Okay. So it's much more close to reality as soon as you add topography into the model. Okay. Then I made a mistake. I realized I made a mistake here because I gave you the notes with exercises and the solutions of the exercises. Okay. You were not supposed to see these boxes, which are the solution of the problems. I think the updated version doesn't have the solution anymore, but you have printed them. So those problems will not go into the exam.
Oh my god.
Okay. I did a mistake in Batik. You didn't, right? No. So the notes that I see there are just. Okay, so those were the initial theories for the wind-driven jars. So they're simplified, but they explain gradually all the main ingredients of the wind-driven jars. This vegetative interior, the existence of a boundary current, the fact that the boundary current is on the west. It included at the beginning a linear bottom drag. That doesn't make much sense, as we will see. The wind driven is not felt all the way to the bottom. And so Munk added horizontal biharmonic viscosity on a side. And that was much more, let's say, closer to reality. And then we actually saw that if you add topography into the system, then the friction is not that important anymore. So the fact that the fact that the first theories were using friction in order to balance the vorticity within the wind-driven jar was not justified. So once you add topography, that bottom stress drag gives you the input of vorticity in order to maintain a western boundary current. And friction is not that needed anymore. Okay, so that was a horizontal explanation. So it was always a homogeneous ocean or a vertical integrated ocean. But now we're going to see how deep can you feel the wind stress or the wind stress curl into the ocean. So basically, how deep is this wind-driven jar? So we're looking at this wind-driven jar, and we were talking of a vertical integrated ocean, but obviously the wind stress is not felt all the way to the bottom. So there must be a scale that you can derive for the thickness of this wind-driven jar. And below this wind-driven jar, there will be another different circulation, which is actually the meridional overturning circulation that we will see later. So now we're going to see a few attempts of deriving scalings of the depth of the wind's influence. Okay? So we can start with the thermal wind equations that you know. Where you have minus okay, so B is buoyancy, is minus G rho prime over rho naught. And this is the thermal wind equation. So you have a meridional gradient in buoyancy or in temperature, and that meridional gradient, horizontal gradient in temperature or buoyancy, will induce a just trophic flow. And actually you can look at the vertical derivative of that meridional flow, and that's the thermal wind equations, right? So if you do a scale analysis of this, you get U over H. It goes like dB over L. Okay? And so H is going to be U dB over L. So there's an F. There's and F, so you want to know H, and H is going to be ULF over delta V. Okay, so that's a scale for the vertical scale. So now we want to relate this vertical scale H to the Ekman pump. Okay, because we know that in the wind-driven gyres we're going to have a vertical velocity related to Ekman pump, right? So a vertical Ekman pumping velocity. And so in order to do that, we go back to the linear geostrophic equation, which was the dV equal the F du by dz, where the W there, the vertical velocity, is the Ekman vertical velocity, right? That was the linear geostrophic vorticity equation. If you do a scaling of this, it's beta u F, okay, where the vertical velocity is the Ekman vertical velocity. So u is F over beta Ekman vertical velocity over h. Okay, so now you put this u into the h scale, and you get FL over delta b, and then the u is f, so f squared over beta vertical velocity over h, so it's an h squared, and so h is f squared over L, Ekman vertical velocity over delta b beta no, I went too far. No, that's fine. Okay, so h is the in this case h would be the depth of the wind's influence, and L is the horizontal scale of the wind-driven gyre. Okay, but having delta V, so the change in buoyancy, the horizontal change in buoyancy, is not really what we want to work with. We would like to see a vertical dependence of this H. And to do that, we're going to look at the stratification. So we're going to try to relate the horizontal change in buoyancy to the vertical stratification to get an estimate of H as a function of the vertical Ekman pumping and the vertical stratification. Okay, so we look at the thermodynamic equation, which, if you remember, was the Lagrangian derivative of buoyancy plus vertical velocity n squared equals 0, where n squared is the Room-Weisart frequency. Right? So that's the thermodynamic equation. You do a scaling of this, and you get u over L, the delta B, plus vertical velocity n squared equals 0. So that delta V goes like the vertical velocity, which is again the Ekman vertical velocity, n squared L over u. So this is my new horizontal gradient buoyancy, now as a function of the Ekman vertical velocity and stratification. So now we're going to use this, and delta B is going to become Ekman vertical velocity n squared over L over that u, which is left and beta h vertical velocity. This goes with this. So you should get n squared beta L h over f squared square beta h over. Okay. Now we plug this delta B into this, and we find that h is now, this is a cube, right? Beta squared and squared to the 1/3. Okay, so this is now my new estimate for the that influence of the wind stress, which is now a function of the Ekman vertical velocity and the stratification. Okay? So this is an estimate you could use to look at the depth of the wind influence. You can plug some numbers there, and you can try to see if h makes any realistic sense or not. Okay. But actually, what we're going to do is derive two different scalings, which are going to be a diffusive scaling and advective scaling. Okay? So this scaling was derived with the thermal wind equation. Now what we're going to do is use the planetary dystrophic equations, which are going to give you two different scalings, one for the diffusive thermocline and one for the advective thermocline. Okay, and we'll see how they relate to this initial scaling. And you can put some numbers here and see how this scaling relates to the ones that we're going to look in a second. So let's rewind a little bit and see what the situation that we're trying to look at. Okay. So if we have a depth at which the wind stress is felt, and below that the wind stress is not felt, then there will be probably some mixing, right? And there will be some stratification. And so you will assume that there will be some regions where you have warmer waters, for example, at the top, and colder water at the bottom. And then you will form what you probably know as a thermocline. So if you start looking at what is reality, and you try to simplify a little bit, so you suppose that there is a net surface warming at low latitudes, okay, which makes sense, and we'll see a schematic there, and net cooling at high latitudes, okay, so you get more warming close to the equator, and a net cooling at the high latitudes. And this maintains a meridional temperature gradient, which is my delta B, or my meridional buoyancy gradient. Okay, so we can thus presume that there will be water rising close to the in the low latitudes. Okay, so this is Z. You have net warming here, and you have net cooling here. So if you have net warming there, then you can suppose that where is this? Yep. So you then presume that there will be water rising at the surface. Okay, here it's warming, so water gets warmer, less dense, and will rise. And returning to polar regions where they actually sink because they become colder, dense, and they sink. Okay. So I think of the circulation, then they go towards the low latitude where they become dense and they sink. Okay. The axis of this meridional returning circulation, we'll see, so this is the basic convective cells explaining some part of the meridional returning circulation, will set a balance between the upward motion, okay, and a downward diffusion. Because if there is net warming here, there will be some diffusion that we will call, with some parameter kappa diffusivity, that will try to mix the waters that are actually these cold waters that are coming towards the low altitudes, they get mixed through diffusion, they become warmer, less dense, and they start to rise. Okay? So there will be a balance between this upward motion and this diffusivity directed downward. Okay? And that will be responsible for the depth at which density will change very rapidly in the vertical. So wherever you meet a balance here, then is where you are setting basically the thermocline. Okay? So that's the region where density will change very rapidly in the vertical. So here is very cold, here is very warm. There will be a region where there is a strong mixing and this cold water becomes warmer. Okay? And there's actually a region where the density or the temperature changes very rapidly, and that's the thermocline. Okay. So after the cold water has sinked at the high latitudes, so here, what is happening? There's very cold and very dense water sinking to the bottom, and through hydrostatic balance, dP by dz minus rho g, then this very dense water will generate high pressure in the deep ocean compared to the one at the lower latitudes. Okay? And so this water, because that water at the low latitude is much warmer, and so for this region the bottom water will start to move towards the equator. Here the pressure is much larger than here, and you're going down the gradient and you start moving towards the equator. That's why the dense water after sinking will start filling the bottom of the ocean, moving towards the equator, okay? Because you are generating, yes, because you...
How is the cold water from below coming up? Is it because of the wind moving the warm water this way?
No. So we're saying here the water goes towards the high latitudes, there is net cooling, becomes very cold, dense, and goes to the bottom. Then you use hydrostatic balance. This is much denser than this one. There's higher pressure here than here, and so this water starts going towards the equator, towards the low latitudes, whatever. And then here you have net warming. Okay, so you have warming here and you have cooling. So if you have cold water here and warm water here at the surface, then there will be some diffusion acting. Okay, and so there is a region where this diffusion is strong and is actually mixing this cold water, which is becoming warmer, and by becoming warmer will start to rise to the surface. Okay? And so it will start to rise to the surface. And so there is a region there will be some upward motion and there will be some diffusion kappa, okay, between the warm water here, this is warm and this is cold. Okay, in between the two there will be some diffusion that we're going to call with a parameter kappa some added diffusivity. And this diffusivity, which is balancing the upward motion, so the diffusivity is directed downward and the upward velocity is obviously directed upward. Okay, and so some of this cold water will become warmer and will rise to the surface.
Does it sometimes become warmer than the upper waters? That is how they will be able to come up to the surface. Because if
it will never become warmer than the one. So
the diffusivity is active to reduce the gradient of temperature in the vertical. So if
it will become as warm as the one at the surface, never warmer.
Okay.
So as this water as this water moves, it is warmed by heat diffusion from above, so diffusion is directed downwards, okay, this kappa, keeping the circulation going, okay, because otherwise you have just cold water sinking to the bottom, filling the abyss and staying wherever it is. You have warm water at the top, warm water at the top, cold water at the bottom, and then it will stay as it is. But you have diffusion that turns this cold water into lighter water. Okay, and so you keep the circulation going. And so there is a vertical density or temperature gradient throughout the basin. Okay, so this is the region where density or temperature changes very rapidly, and the cold water is turned into warm water through diffusion. But this is not happening in polar regions, because in polar regions, here the water becomes very cold, very dense, and sinks to the bottom. So all this region is very homogenized. There is no stratification here. So this region where the density or the temperature changes very rapidly is going to look a little bit like this through diffusion processes. Okay, so this is a much nicer schematic of what I'm talking about. So you have water going towards the higher latitude, becomes cold, and sinks to the bottom. And this is very well homogenized. Okay, then the dense water displaces light water and moves towards the equator through hydrostasis. Okay, and then when it reaches this region where you have warm surface water, then there is heat diffusion that warms the cold water, and the water starts to be warmer and rise to the surface. Okay, so this is a simple diffusion argument of this single cell, just through difference in surface buoyancy flux and diffusion in the interior. Okay, so given this very simple picture, then if we think about this balance between upward motion and diffusion, then we can start to think about a different scaling for the depth of this thermocline. And it's going to be a kinematic scale. Okay. So if you think of this simple advection and diffusion process here, setting the depth of this region where the stratification changes very rapidly, then you can consider an advective and diffusive problem, which you have solved numerically in numerical methods, I think. So you have W dt by dz, some eddy diffusivity parameter dt by dz. Okay? So this is an advection diffusion, simple advection diffusion process. So W is the vertical velocity, kappa is an eddy diffusivity, and T is the temperature, of course. Okay. So the vertical velocity is positive. This vertical velocity is positive. And so that means that vertical diffusion is negative, directed downwards. Okay. So if we take vertical velocity and kappa to be constant, just to make things simple, and then we take the temperature is temperature at the top at z equals 0, and temperature is temperature at the bottom at z minus infinite. Okay, so very deep. Then we can solve that equation, and that equation is T equal T top minus T bottom, z, the vertical velocity over the diffusivity plus T at the bottom. We just solved that equation after those two parameters are set to constant, the vertical velocity and the eddy diffusivity. So the temperature falls exponentially, okay? And the E-folding scale is, you can call it delta, which is kappa over the vertical velocity. Okay? So this is the E-folding scale for the exponential decay of the temperature. Okay, and so we are looking at this schematic of the thermocline. So you have a jar at the surface, which we know how it forms, you have some cold water in the northern regions that it convects, fills the abyss through hydrostatic balance, and then through some diffusive processes gets warmed up and becomes lighter water. Okay? And so there is a region where there is an advective diffusive balance here between the upward motion, the upward vertical velocity, and the diffusivity directed downwards, where the stratification changes very rapidly, and that is what we're trying to set as the depth of the thermocline. Okay, so this is the first estimate of the thickness of the thermocline that we reached, and we can try to put some numbers here. So if we put a vertical velocity of 10 to the minus 7 and a diffusivity which is close to observed values of 10 to the minus 5, and you put those numbers here, then in this case you get a delta which is something like 100 meters. Now if this is 10 to the minus 4. And if you put 10 to the minus 5, you get a thickness which is something like 1,000 meters. If you put those numbers there. So 100 meters is definitely too thin, okay, but actually corresponds to -4 and 10 to the -7, so this is 10 to the 3. Yeah. Okay, so observed values are on the order of 10 to the minus 5. And it gives you a thickness of the thermocline which is something like 100 meters, which is too thin. If you use a much higher eddy diffusivity, 10 to the minus 4, which you can find somewhere in the ocean, but as an estimate, as a global average, is way too large, then you get an estimate which is closer to reality, 1,000 meters. So the advective diffusive scaling for the thermocline is probably not the best to explain the observed thickness of the thermocline, but at least it's telling you something. What it's telling you is that an advective diffusive scaling, what it's telling you is that the temperature gradient is concentrated in the upper ocean. Okay? So it's not much of a result, but at least it's telling you that this thermocline is not at 2,000 meters, okay, or 3,000 meters. It could have been, okay, but if you use realistic values for the vertical velocity and a range of eddy diffusivity, it gives you very different results, but both results will be in the upper ocean. So what it's telling you is that the thermocline is set in the upper ocean. Okay. So if you think that there is a jar here, you know that the influence of the wind stress, and so the jar is not going to reach very deep layers. It's going to stay in the upper ocean. And now we will refine this scaling anyway. Does this make, so how do we know how thickness is the thermocline? You can actually look at observations. Okay? So if you look at the Pacific or the Atlantic, you always get the same result, of course. So if you look close to the equator, you see how shallow the equatorial thermocline is. Okay, so it's basically here. Okay, and that's because actually when you reach the equator, then you have upwelling in the equatorial regions, right? And so this is very shallow. When you go towards mid-latitude values, so where we are in subtropical regions, then you get a thermocline which is, it reaches on the order of 1,000 meters or so. So you have a homogeneous layer here, the mixed layer, then the temperature changes very rapidly, and then you have a quasi-homogeneous ocean. Okay, so this is my thermocline, and it's in between 500 to 1,000 meters. When you go to 35 north, you get the blue line, and this is my thermocline that actually goes down to 1,000 meters. Then when you reach the northern regions, you see that the thermocline is gone, and that's because you're close to a homogeneous place where there is a lot of convection. Okay, and the same thing in the Atlantic. Okay, so we know from observations that the thermocline is on the order of 500, 1,000 meters. So it's an upper ocean thermocline.
What agency going to come to the conclusion that the depth of the thermocline is below 1,000? Is it the distance it takes for the rock to become perfectly vertical, or because if you look at it, for example, around the equator, it's about become perfectly vertical around 2,000 depth.
Yeah, but the thermocline is a place where temperature or density changes very rapidly. So I'm not saying that it doesn't change, but it changes very rapidly. So you have a mixed layer, then you have a thermocline, and then this continues to change. So this is your thermocline. You can say, you can decide that the thermocline finishes here or finishes here. Right? Then you can look at the pycnocline, the halocline. You can set the thermocline depth to whatever. But the point here is that it's an upper ocean thermocline. It's on the order of 1,000 meters. And you see the change in the depth as you move towards the northern latitudes, where you basically don't have a thermocline, and it's very well homogeneous. Okay, so that's it. So now we're going to derive a more refined scaling for the thermocline. So we will separate a diffusive thermocline and an advective thermocline. We'll see that the diffusive thermocline is going to be very similar to this. And then we will see the advective thermocline. And that will give you an estimate for the depth and the depth influence and the thermocline, but obviously not a precise estimate. Okay? So what we're going to do is use the planetary geostrophic equations, which are those ones. Okay, we've seen them before. You have the momentum equations. You have hydrostatic balance, the second one, you have continuity, and then the thermodynamic equations. Okay? And now we're going to look at first a diffusive scale and then an advective scale. Diffusive. And the difference here is that we're going to have an information for the equant velocity. So how can you derive a diffusive scale? Suppose there is no wind stress at the surface. So like in this case, you just have differential heating, but no wind stress. Okay? So you only have diffusive processes. And so the only possible driver is diffusivity. So what would be the depth of the diffusive thermocline in this case? So we again use an advective diffusive balance as before. You take the curl of the momentum equations, those ones that we did last time or 2 times ago, so I'm not going to do it again. You take the curl of the momentum equation, use mass continuity, and you obtain a linear vorticity balance, which we know is this. Okay, take the curl of the momentum equation, use continuity, and you get a linear vorticity balance there. Then the kinematic equation is this, and then you have the thermal wind equation. Okay. So you have the thermal wind, and you have the vorticity, okay, and the kinematic equation. So if you do the scaling of all this, you get a W here over some delta, this H, that now we're going to call delta, K over delta squared. For the vorticity, you do a scale analysis, you get beta, U and V are the same, so it's BU, F over delta. Then here you have F, U over delta equal my delta B over some L. Okay. So this, for the kinematic, is just a diffusive scaling as we did before, so it looks exactly the same as the one before. Okay. So this is delta kappa over vertical velocity, just as we did before. But now we have an information for the equal vertical velocity that we can use. So my vertical velocity W is beta U delta over F, okay. And U is delta B F delta L. So if you put this U here, you get a vertical velocity which is beta delta squared my delta B over F squared L. So this is my scaling for the vertical velocity. If you now put this scaling for vertical velocity into the scaling for delta, then you get that delta is equal to kappa F squared L over beta delta B 1/3. Okay? You can just plug things into the scaling for delta and you get to this. And so if you use this delta here, then now, so this is my delta and my vertical velocity. After you use this delta, is going to be kappa squared beta delta B over F squared L 1/3. Okay, just rearranging things. So this is my scaling for the vertical velocity, which is this, and this is a scaling for my thickness of my diffusive thermocline delta. Okay, so in a diffusive scaling only, so we said there is no wind stress at the surface, there's only diffusive processes. What do they look like? So we can use typical values that are realistic enough. Okay, so the horizontal change in buoyancy is something like 10 to the minus 2 meters per square second. L, the horizontal scale of the jar, is something like 5,000 kilometers. F is 10 to the minus 4, and kappa we said is 10 to the minus 5, is more realistic, 10 to the minus 5. Okay? So if you plug those numbers into the scaling for the thickness of the thermocline and the vertical velocity, you get numbers that are close to 150 meters for the depth of the thermocline, and a vertical velocity, which, if you remember, is the Ekman pumping. of something like 10 to the minus 7. Okay, so let's put this here, 150 meters, and this is 10 to the minus 7. Okay, this is for a diffusive only thermocline. Okay, but the vertical velocity, the Ekman pumping velocity, is 10 to the minus 7, which is way too small. Okay, the observed values are between 10 to the minus 6 and 10 to the minus 5. So this vertical velocity, which is in balance with the vertical diffusion, in a simple advective diffusive scaling, is too small. If you use, that's supposed to be kappa 10 to the minus 4. Okay, this is a mistake. Then you get a delta, which is something more realistic, 700 meters. But the vertical velocity, the Ekman pumping velocity, is still too weak. So just an advective, just a diffusive scaling for the thermocline is not enough to explain the observations. So we're going to need something else, which is an advective scaling. I'll try to do this here. Okay, so just the diffusive scaling, considering no wind stress at the surface, gives you an advection diffusion balance that predicts an Ekman pumping velocity and a thickness of the thermocline, which is too weak. Okay. So we use the same planetary, where are they? This one's the same planetary Stoffic equations, okay? But now that we got to that conclusion, that the Ekman pumping velocity through the diffusivity is too weak, then we're going to say, okay, then we can ignore the diffusive term and the thermodynamic term completely, because that gives me an Ekman pumping velocity which is much too weak. And so we derive a scaling which is now totally adiabatic, okay? So there's no diffusion. And we're going to try to see if we can get an estimate of the depth of the wind's influence that is more close to reality. Okay? And also because there is so in an advective diffusive balance, you have a vertical velocity directed upwards, and you have a vertical diffusivity directed downwards to balance the vertical velocity, right? But in a wind-driven gyre, something like this, where is the vertical Ekman velocity directed? No, the hemisphere, subtropical gyre. We're talking about the hemisphere and subtropical gyres. Where is the Ekman? What is what? Where is the Ekman pumping or vertical vertical Ekman velocity directed to? Downwards, right? And so if you have a diffusive balance, where is kappa, the vertical diffusivity, directed to? Upwards. Okay, so this is when you don't have wind stress. Okay, you have just differential heating at the surface, and you have a diffusive balance. In this case, you have diffusion directed downwards, which creates a vertical velocity towards the surface. In a wind-driven gyre, you have vertical velocity directed downwards, and to find a balance, you need vertical diffusivity directed upwards. Okay? And at some point, you will have a vertical velocity which is equal to 0, which is in total balance with the eddy diffusivity. And that's the depth that we are going to trying to find, the depth. So I deleted the equations, but you take the same planetary Stoffic equations, but we said that we're going to ignore the diffusivity terms and the thermodynamic. So we are simply left with the second one, which was the linear geostrophic balance and the thermal wind. Right? So we deleted the thermodynamic equation. So if you do a scale analysis of this, is again beta u f over d. Now is an advective vertical scale, so we're not going to call it delta. This was the diffusive scale. Now is d, some advective scale. And here we have u over d, which is equal to, again, delta b over fl. Okay, and this vertical velocity is now the Ekman pumping, which we know where it is directed to. So now you rearrange all of these things and you get to a scaling which looks like this. Okay, so now this advective scaling, if you rearrange between one and the other, you get a D, which is this. So now this advective scaling is telling you two important things. So first one is that increases with the magnitude of the wind stress, because the Ekman pumping is proportional to the curl of the wind stress. So obviously, the stronger the curl of the wind stress, the larger the Ekman pumping velocity. Okay? And so the larger the Ekman pumping velocity, the more you squish down the isopycnals. And so the deeper it gets, the thermocline. And then the second one is that it decreases with the meridional temperature gradient, this delta B. Okay? If delta B is large, then the thickness of the thermocline diminishes. And that's because, if you think about it, is because a larger temperature gradient, so if delta B increases, that makes the vertical shear larger, if you remember the thermal wind shear. And so the horizontal transport is fixed by mass continuity. And so the only way to maintain these two, a larger vertical shear and the same vertical transport, is that the vertical scale decreases. And so it's more confined to the surface, and so this D has to decrease. If the horizontal gradient in temperature increases, vertical shear increases, and so this D gets shallower and shallower. Okay, so now this is my D, my advective scale, and if you put some realistic numbers, if you put some realistic number for the Ekman pumping, something like 10 to the minus 6 or 10 to the minus 5, what would be the depth of the wind influence region D? So for Ekman pumping, 10 to the minus 5, D is 10 to the minus 5, this is 10 to the minus 8, that's, I chose 5 times 10 to the 6, that's the horizontal scale of the wind-driven gyre. Beta is 10 to the minus 12, and delta B was 10 to the minus 2 to the half. This is, if you do the numbers, this is roughly 700 meters. If you choose an Ekman pumping of 10 to the minus 5, then D is 10 to the minus 5, 10 to the minus 8, 5 times 10 to 6, 10 to the minus 12, 10 to the minus 2 to the half, and this is roughly 2,000 meters. Okay.
Is beta 10 to the minus 11 or 12?
Beta 11, oh 11, sorry. Okay, so you get an advective scale for the depth of the thermocline, which is, depending on the Ekman pumping that you choose, 10 to the minus 7. This is too weak, okay, so the diffusive scale cannot explain an Ekman pumping, a realistic Ekman pumping. A realistic Ekman pumping is between 10 to the minus 6 and 10 to the minus 5. So given this Ekman pumping, you get a depth of the thermocline, this depth, which is on the order between 700 meters and 2,000 meters, which is much more realistic if you look at this picture over here, okay? Between 500 and 1,000, 1,000 and something. Okay? If you look at the Atlantic, it goes deeper than 1,000 meters. So the advective scaling for the thermocline is definitely a better scaling for the depth of the thermocline. But actually, this one is not to be discarded, because actually this is telling us something else. So this is the depth of the thermocline, in the sense that you have a gyre here, okay, which is driven by the curl of the wind stress. This curl of the wind stress is inducing an Ekman pumping, in this case directed downwards, which is squashing down the isopycnals, and it will create a thermocline of depth d. Okay, so this is the depth at which the wind is felt by the ocean, because in this case we are considering the Ekman pumping. Okay, so that's the depth of the thermocline. This instead, so this is the depth. This instead is in an advective diffusive process. So we are here, and that delta is the thickness of the thermocline. So where diffusivity is important. You have warm water here and you have cold water below. And there is a region where there is mixing, where kappa is mixing the two waters. Okay. So how thick is that mixing layer where mixing processes exist? Above of that you have warm water, below that you have cold water. In between you have a region where diffusivity is mixing the water, and there is an upward velocity between the cold water and the warm water. So that, without winds, that's just a diffusive process, is this delta, which is actually the thickness of the thermocline. Okay, so if you don't consider wind, you just have differential heating at the surface. Then you will have warm water at the top, cold water at the bottom, and some region where there will be some mixing processes. That region can be very large or very thick or very thin, where you have mixed waters, okay, depending on the diffusivity. And so that region where diffusivity is mixing the waters has a thickness, and that thickness is given by this scaling. If you actually consider a wind-driven gyre, so a wind stress at the surface, you have an Ekman pumping, which is squashing down the isopycnals and is actually causing a thermocline, and the depth of that thermocline, or in other words, the depth at which the wind is felt, is given by this d, and this d is therefore the depth at which the wind is felt, or the depth of the thermocline. So you will have to take into account both the depth of the thermocline and the thickness of the thermocline. So here you're squashing down the isopycnals through Ekman pumping, and so you form a thermocline. Then how thick is this thermocline? It depends on the diffusivity processes, which are considered in this separate model. Obviously you have both acting at the same place. So first you create a thermocline, and then that thermocline is very thin, so there is a sharp distinction between the cold and the warm water, or this thermocline is very thick because there is a large region where diffusivity is acting. So you have two things: you have the depth of the thermocline, and you have how thick this thermocline is.
The direction of the heat diffusivity is ultimately confusing for me, because where is the heat coming from and why is the heat diffusing from cold to hot?
Because you need to find a balance between the vertical velocity and the diffusivity. If the vertical velocity is directed downwards, then you will have diffusive processes in the opposite sense, and at some point both will balance each other. So in a simple diffusive process, you have warm and cold, and diffusivity is acting downwards and vertical velocity upwards. If you have a vertical velocity that is actually acting downwards, then diffusivity will be in the opposite sense. I think I talk about this here somewhere. So in the this is a isotropical gyre example. Okay, so the Ekman pumping is downwards, and so the diffusivity velocity must be upwards in order to balance each other. And so this implies that at some level d, which is the depth of the thermocline, the vertical velocity must be 0.
This one has more notes. This one has more words than this.
That's why you should look at the updated version. Okay. So to summarize, the wind influence can be understood from the advective scaling, and so you get a depth d of the depth influence, which is directly wind driven. Okay, and so it's how deep can I feel the wind is given by this depth d, where I have the Ekman pumping directed in this case downwards. Over the depth d, we expect to see wind-driven gyres. So between the surface and the depth d is where I have a wind-driven gyre, which can be something like 700 to 2000 meters deep. That's where I feel the wind. Below the d, that depth of that thermocline, is the abyssal circulation. So in this case, here you have water sinking in the northern latitudes, then filling the abyss, and then there will be some mixing processes, and the upper layer is governed by the wind-driven gyres, whereas this one is governed by the meridional overturning circulation. The thickness delta, instead, this one, is the diffusive transition region between the two different water masses. So it's this, okay? This is my delta. So I have the cold water here, I have the warmer water at the surface. The depth is d, but how thick is this transition region, how thick is my thermocline, is given by a diffusive process, and that is given by this thickness delta, which is separating a warm subtropical water, in this case we are subtropical gyres, and the cold, dense water that sunk in the northern hemisphere and are trying to upwell in the wind-driven gyres. So d is the depth of the thermocline, and delta is the thickness of the thermocline. And this is a nice schematic that summarizes what I was trying to say. So you have an Ekman pumping directed downwards in a subtropical gyre, okay, and that creates a depth of a thermocline, okay. Below this d, I cannot feel the wind. Then how thick is this thermocline? That is given by delta. And this is where I have those diffusive processes that are taking my cold water into warm water. Okay? So this is the region where I have all these diffusivity processes. Could be very thick, could be very thin. But the depth at which these diffusivity processes are acting is given by the Ekman pump. Okay? So I'm squashing down my isopicnons and I create a thermocline, which could be a 1000 meter then that thermocline could be very sharp or it could be very thick, and that depends on the diffusivity. Okay, so one thing is the depth of the thermocline, and another thing is how thick is my thermocline. I could have, in this case, I could have a thermocline which is like this. Okay, this is Z, and so it's very thin, and this is warm water and this is cold water. Okay, or I could have a thermocline that is actually very thick. Okay, but there's a lot of mixing after that. So it could be a very thick region where diffusivity are acting and are mixing cold water into warm water. Okay. It could be very sharp or it could be very thick. But one thing is the depth, and another thing is the thickness delta. Okay, so the thickness delta is given by the diffusive scaling, and the depth of the thermocline D is given by the advective scaling, which is where you are taking into account the Ekman pumping. So the Ekman pumping is squashing down this thermocline until some depth D, depending on the Ekman velocity. And then how thick is this thermocline? Could be very thick or it could be very thin, and it depends on a diffusive scale, which is proportional to it was proportional to the kappa, right? It was kappa vertical velocity. So we know that the thermocline is an upper ocean phenomenon. Okay, so it's concentrated in the first 1,000 meters or so. And then how can we give some scaling for this thermocline? We can have a diffusive scaling, which explains how thickness this thermocline is. But then we know how thickness it is, but where it is in the column of the ocean, that is given by an advective scaling that is telling me how deep this thermocline is. And the depth is where I feel the wind influence. Okay, below that, I cannot feel the wind stress curl, and so the ocean is not governed by the wind stress curl, but below that depth D, you have this abyssal circulation, which is governed by other dynamics, which is basically the meridional overturning circulation. So you have a wind-driven gyre at the surface, which has a depth D, which is the depth of the thermocline. Below that, you cannot feel the wind. You actually have meridional overturning circulation, different circulations. Okay. And that depth of the thermocline, that depth of the wind-driven gyre, can be thick or it could be thin. That separation between the wind-driven gyre circulation and the meridional overturning circulation. And it's going to be thicker or thinner depending on diffusivity. And to give an example, there is not just one thermocline, but there is the permanent thermocline, there is the seasonal thermocline. So obviously depending on the wind stress curl, depending on the season, the wind stress curl changes. So the thermocline will move up and down, right? Because the depth D will change depending on the wind stress curl. In winter, in summer, the wind stress curl doesn't have the same magnitude. So the thermocline, there's a seasonal thermocline that goes up and down, and the thickness of this thermocline can also change because the diffusivity is not always the same depending on where you are. So the thickness of the thermocline could be thicker in, I don't know, in one place, and as you move north it could be thinner. So it doesn't have to be the same thickness because diffusivity is not. We took diffusivity to be a constant, but it's definitely not a constant. Okay, so depending on where you are, it could be thicker or thinner. And then you also have a seasonal thermocline. But just to give a scaling and a rough idea of how deep you feel the ocean and how thick is this transition between the wind-driven gyre and the meridional overturning circulation, these two scaling are enough. So have a look at the updated notes. See you Monday, right? Yes.
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 Okay.